In this video, we'll be talking about the 2018 number 6 BC question, the Taylor-Maclaurin question for it. So they give us a Maclaurin series for natural log of 1 plus x. So they gave that to us, which was nice of them. On its interval of convergence, this series converges to the natural log of 1 plus x. Let f be the function defined by f of x equals x multiplied by natural log of 1 plus x over 3. So they're pretty close, just a couple little tweaks we'll have to make. Part A, they want us to write the first four non-zero terms and the general term for the Maclaurin series for f. So let's go ahead and just copy down that natural log of x function. Natural log of 1 plus x, that's the stock function that they gave us. So I see a couple tweaks in here. I see there's a multiplied by x on the outside. I also see there's an x over 3 on the inside as opposed to just a basic x. So let's first substitute in that x over 3. I like to do that inside part first. So we're going to go ahead and replace every x with an x over 3. So every x in that top equation will get an x over 3. A little bit cumbersome, but that's what it would look like. And then, of course, we can just simplify that just a little bit, basically getting rid of these crazy fractions inside of fractions. And so I will square like that term out and mix it with the 2, or cube this term out and mix it with the 3. So that's what I'll do next. So it should simplify to that when you're all said and done. And so that would be natural log of 1 plus x over 3. So we're pretty close. Now all we have to do is multiply every term by an x. So basically we're going to bump all of those powers of x up by 1. So that should turn out to x squared over 3 minus x to the third over 6 all the way down the line. The tricky part I think here is maybe at the end. Notice this x does change to an n, x to the n plus 1. It was x to the n power, and so we have to add 1 to that or raise it by a power because we multiplied every term by an x. That's why it's an n plus 1 right there. In part B, they want us to determine the interval of convergence for the Maclaurin series of f. We're going to show our work that leads to that answer. So interval of convergence, want to make sure that we check the endpoints. We'll find the radius of convergence, and then we'll plug in both endpoints to see if those are going to work. So we're going to write the Maclaurin series. I would write this in sigma notation. So that's what I'll do first here. I'm taking my general term from part A, and I'm going to use the ratio test to figure out what my interval of convergence is. Now remember, the ratio test is the replace every n with an n plus 1, and then we'll divide by the original. That gets a little cumbersome, so I usually multiply by the reciprocal of the original. So this would be my general term with an n plus 1, and then so that's this thing right here. And then this part is the original one flipped over, just so I can do some of that canceling. So we're going to do kind of some of that canceling. If there's extra things on there, we're going to cancel them out. We do have the alternators in there. We didn't really need to do that. You can put that in there, but it's absolute value, so it's going to make all of that positive anyways. But I went ahead and left it in there for this video. So we're going to do some of our canceling here. And it should reduce down to this. Limit as n goes to infinity, negative x multiplied by n all over n plus 1 multiplied by 3. So as n goes to infinity, these are both n to the first powers. And so that will tend towards its leading coefficients, which is negative x over 3. So that should be what's left over for this one. X over 3 less than 1, we could multiply by 3 on both sides. It's got to be bigger than negative 1. So my radius of convergence is 3. That's how far it can travel and still work. And now we got to check both of the endpoints. So that's what we'll do next. Check both the endpoints by plugging in x equals negative 3 for x, and we'll do x equals positive 3. We're basically seeing if those can work, or if those series will converge at those endpoints. We know it works for everything in between, but we're going to check those endpoints. So if I plug in a negative 3 for the x, on that I get this negative 1 to the n plus 1 multiplied by negative 3 to the n plus 1 all over n, and then 3 to the n. So we can combine those a little bit. The negative 1 and negative 3 are both being raised to the n plus 1 power, so I can multiply those two together. And so that would give me 3 to the n plus 1 all over n multiplied by 3 to the n. A little bit of reducing, and I get 3 over n, and that would diverge because of the p-series test. That's the easiest test to use. You could also use the integral test. That integrates to natural log, do an improper integral, and that's fine as well. So that one does not work. That one diverges, so I don't want to put an equal sign on the negative 3. So let's go ahead and check the right endpoint now. So we're going to plug in a positive 3. So when x equals 3, we'll plug that in. A little bit of reducing on that, 3 to the n plus 1 over 3 to the n. I can cancel those out, so I get 3 over n. Now that is an alternating series test, and since the term itself, 3 over n, tends towards 0, goes towards 0, and it's an alternator, that will converge. It is a conditional convergence, but it still does converge. So we're going to go ahead and put an equal sign underneath the positive 3. So my interval of convergence for f is going to go from negative 3, less than x, less than or equal to 3. In part C, they said let P of 4, so the fourth degree polynomial approximation, be the fourth degree Taylor polynomial for f about x equals 0. So they want us to use the alternating series error bound to find the upper bound for P4 of 2 minus f of 2. So that's basically saying that your approximation of fourth degree at 2 minus the actual function value. I want to find the difference between those two, or my error. So I'm looking for the error between those two. So first, let's go ahead and write the fourth degree Taylor polynomial. So the fourth degree Taylor polynomial, well, technically that's the fifth degree right there. I just want to use the first 4 evaluated at 2. Now you don't have to do this part, but I'm just trying to show like what this would look like. So the polynomial of fourth degree at 2 would be if I just plugged a 2 into that to that function right there. So I'm not going to simplify that. I'm just saying that that would be my approximation for 4. Now the actual function value, I want to find out the difference between those. So the alternating series error bound test, once again, that is the approximation error bound is less than the absolute value of the next term, or the first term that you didn't use. The first term I didn't use is that x to the fifth over 324. It is absolute value, so I'm not worried if it's positive or negative. It doesn't really matter. It's whatever that term happens to be. So I'm just going to plug a 2 into that first unused term. So kind of messy, but that absolute value is less than or equal. Let me sneak an equal sign in there, to 2 plugged into that first unused term, which is just 2 to the fifth over 324. You don't have to simplify that. That's good. That's the accuracy level, or that's how far, that's the most that your error bound can be.